Okay, lesson 1.13 through 14, part B. So we're still talking about function models and applications. Our skills and learning objectives are still to construct models from a data set and justify, identify an appropriate function type to construct a function model given a scenario, describe underlying assumptions about a model for a given scenario, construct a linear, polynomial, or piecewise defined function to model a scenario, construct a rational function model based on a context, apply a function model to answer questions about a data set, and use technology to find and compare regression equations. All right, so there are times, choosing an appropriate function model. So there are times when we are given the model to be used, but you will also be expected to select an appropriate model based on a given data set or context of the problem. You will need to use a polynomial model of degree 3 or greater, piecewise defined functions, or rational functions. All right, so for each of the following scenarios, determine whether a linear, quadratic, or cubic model would be most appropriate and explain why. So, on A, it says Al's food truck sells Italian panini sandwiches. The price for panini varies between $4.50 and $8.50 depending on the number of items added to the sandwich. The total number of panini sold are counted relative to the price of the purchase. All right, so this one here would just be linear, because the price depends on the number of items added to the panini. So price depends all right, and those would have a constant price, so it's an additional so much per item. All right, B. Helen's helium balloons is filling spherical Mylar balloons on your 16th birthday party. The radius of each balloon is measured relative to the amount of helium it contains. All right, so they're talking about the amount of helium they're putting inside. They're talking about volume. Okay, remember volume is measured in cubic units. So therefore, this is cubic. Okay, the context is related to volume. So if it's related to volume, you know it's going to be cubic. Area would be quadratic. All right, so C says a buoy is placed in the harbor with a beacon light mounted at the top to warn boats to know where the harbor begins. The light can be seen from a distance of 1/4 mile and rotates in a circle manner every 3 seconds. So here's our buoy, and so it can be seen anywhere in this shaded area, okay? Shaded area. So we're talking about area there, which is where it can be seen. And so because it's area, remember area is measured in squared units. And so square is a quadratic. So context relates to area. All right, example 9 says consider the table given below. The table provides data for 5 ordered pairs x, y. All right, which function type models the data in the table? Linear, quadratic, or cubic? Explain your answer using characteristics from the data in the table. All right, so one way we can look at this is we can try looking at our differences to see if first differences, second differences, third differences are closer. And then we're going to look at a graph. So let's first look at the differences. So if I look from 10.2 to 2.9, we're going down by 7.3. 2.9 to 8.2, we're going up by 5.3. 8.2 to 16.1, we're increasing by 7.9. And 16.1 to 17.9, we're increasing by 1.8. Now let me point out, I'm not worrying about the x's because they're all increasing by even increments. They're increasing by 5 each time. If my increments weren't the same, then I would have to find the slopes here. Do y over x for this first group, okay? Because they're the same, I'm not going to worry on them. All right, so those differences are not close to each other. So it is not linear. So let's try second differences. So negative 7.3 to 5.3, we're increasing by 12.6. 5.3 to 7.9, we're increasing by 2.6. And 7.9 to 1.8, we're decreasing by 6.1. Those really aren't close either. So right now I'm leaning towards not quadratic. So let's check the cubic. And so I'm going to have to do like this. So 12.6 to 2.6, we're subtracting 10. And 2.6 to negative 6.1, we're subtracting by 8.7. So that does seem like it's a little bit off, but they are both going in the same direction. They're both negative at least. If you remember, we had this was increasing by 5. So if we put over 5, this would be negative 2. And this one over 5 would be negative 1.74. So it's a little bit closer. So, but out of all of them, cubic is our best choice, I think, looking at the differences, okay? Because the others, we had negatives and positives all in here. Same thing on this one, we had a negative and then positives. At least these are both negative. All right, so cubic looks like the best fit. The other thing we can do is we can go put this into our calculator. Go put it in our stat edit. All right, but you don't have to run regression because I just want to, well, yeah, we're going to run regression. So go ahead and put it in your stat edit, and we think it's cubic. So let's run cubic regression. So stat edit, X is in L1, Y is in L2. Then go to stat, calc, over to calc, and you're going to choose cubic regression. All right, so when I do this, I'm going to store the equation again in my Y1. So store regression equation and Y1. Remember, you get that by hitting alpha trace. Okay, so pause the video if you need to while you do that. So we've got this in, we've got our equation, we think, but I really want to look at this graph, okay? So we're going to go to second y equals. And I'm going to go into stat plot 1. And I want to turn it on. All right, so if I haven't messed with anything, everything's where it needs to be, but make sure your X list says L1, your Y list says L2. All right, that's the main thing. Now, once you do that, go to Zoom. And if you look down at number 9, it says Zoom Stat. That will fix your window for you. So click Zoom Stat and look at it. Do you see your points? And do you see how your graph is going through all of your points? It goes through most of them. So, actually I think it goes through all of them. So that means that this is a really good fit for the data that we were given. So we're going to say it's a cubic model. So cubic, and explain your reasoning. Third, differences. Are close to 2, or close to negative 2. And the cubic regression equation goes through all the data points. Then it wants us to write the equation of the regression model. Well, it's a good thing we stored it in y equals because you can go back in there and grab it. So y equals should be negative 0.1247x cubed plus 0.4334x squared minus 3.2969x plus 10.1814. And then C says use the model from part B to predict the value of y when x is 25. Go to your table. Go find when x is 25, and you'll find that it's at 3.86. All right, constructing a rational function model. All right, so data sets and aspects of contextual scenarios involves quantities that can vary directly, inversely, or both. Inversely proportional scenarios can often be modeled by rational function. If x and y vary directly, then the data is modeled by the equation y equals kx. Okay, so varies directly. We're going to take, it's always going to be y equals k, and then directly means multiplied by x. Okay, if x is inversely proportional to y, then the data set can be modeled by the equation y equals k divided by x. All right, inversely proportional means to divide. So like I said, you're always going to have y equals k, but then it's inversely, so it's divided by x. And k is known as your constant of proportionality. It's the way that it is changing. Okay, so directly means multiply, proportional, or indirectly, inversely is the other word they use a lot of times. Inversely means to divide. All right, so example 10. So the volume V of an ideal gas kept at a constant temperature varies inversely with the pressure P exerted on it. If the volume of a gas is 200 centimeters cubed under a pressure of 32 kilograms per centimeter squared. All right, A says to find the constant of proportionality, so wants to solve for K and write a function to model the volume in terms of pressure. And then B wants us to use the model to find the volume of the gas when the pressure is 40 kilograms per centimeter squared. All right, so usually when they give us a scenario, it's always set up like this. The first equation is going to set up our equation. Okay, the first sentence sets up our equation. The second sentence gives us everything except k so that we can solve for k. And then the last sentence says, hey, now that you know k, here's some other values for the other variables. Go solve what we're asking for. So if you notice here on the first one, it says the volume is kept at a constant temperature, varies inversely. So there's our equals k. So volume is in front of it. So volume varies inversely, so equals k, inversely means divide, with the pressure P. All right, if the volume is 200, equals k over, and the pressure is 32, solve for k. So multiply by 32, and we get k equals, we got 6,400. Oh, for some reason, there we go. All right, so then our equation there will be V equals, we know K is 6,400 divided by P. Oh, that just 6,400. Sorry, for some reason my pen just was not writing good. All right, B says use the model to find the volume of a gas when the pressure is 40. So you know now that pressure is 40, and you're looking for volume. So you get V equals 6,400 divided by P, which is 40. And so it should give us 160, and volume is measured in centimeters cubed. All right, 11. It says Hooke's law states that the force required to stretch or compress a spring by some distance is directly proportional to the distance. A force of 275 newtons stretches a spring 0.2 of a meter. Again, the first sentence is going to tell us how to show it up, or set it up. So there's the words directly proportional. You're looking for directly, inversely, jointly, which we haven't talked about but exists. Jointly is just multiplying more than one variable with k. All right, so what is directly proportional? The force. So F equals K directly means times the distance, so D. Then it tells us the force of 275 stretches a spring 0.2 of a meter, so you know your distance is 0.2. Divide by 0.2, you'll find K equals 1375. Now, A does say how far will a force of 620 newtons stretch the spring. So we know our equation now is F equals 1375 D. Well, the force is 620, and so we want to solve for D. So divide by the 1375. And so D equals, I got 0.4509, and distance is measured in meters. All right, B says what force is required to stretch a spring 0.1 of a meter. So this is our distance. So well, we still know our equation is still the same. F equals 1375 D. But now I know the distance is 0.1. So 1375 times 0.1. So the force is 137.5, and force is measured in newtons. All right, example 12. Says the expected population P for a herd of buffalo in the Northwest can be modeled by the equation given there, where T is the time in years since 2000. State the initial population for the herd of buffalo. So your initial population is when your time is 0. It's the beginning thing. So we're looking for P of 0. So plug in 0 for T. So we get 112 over 1, which is 112 buffalo. All right, B says, what is the rate of change in the number of buffalo from T equals 0 to T equals 25? Include units, explain the meaning and context. Well, so we want the rate of change, which remember is just your slope. So we need to know, let me actually do this. So we've got two ordered pairs here. So we got 0, comma, we don't know, and 25, comma, we don't know. So we can go find P of 0, which we just said, actually I lied when I said we don't know, it's 112. We just found it. And then P of 25, so we can go find it the same way. And we should get 172.1429. And then I want the rate of change, which is our slope. So our rate of change is equal to our y2 minus our y1 over our x2 minus our x1. And so when we do that, I got 2.4057. The y's are the number of buffalo per, and the x's was my year. Okay, it's the time, so time in years. So what does that mean? It means that the buffalo population is increasing by approximately 2.4 buffalo every year for the first 25 years. So buffalo per year between year 0 is year 2000. Between years 2000 and then 25 would be 2025. Okay. And then C says a function given it's valid for 0 to 50 years. From 2051 to 2100, scientists predict the herd will decline at a constant rate of change of 5 buffalo per year. Write a piecewise function B of t to represent the population of buffalo in the Northwest for the entire century. All right, so B of t equals, well, for the first 25 years, let's talk about that. So what do we know? That their rate of change is 2.4. Well, this is for the first 50 years, though, so I guess I can't really do that one because it's good through 50. So, okay. But they gave us that equation, so I'll tell you what. Let's just use the equation they gave us. So they told us that the 112 plus 2.75t over 1 plus 0.002t, and this is good for 0 is less than or equal to t, less than or equal to 50. All right, but then they told us that from 2051 to 2100, it's going to decline at a constant rate of change of 5 buffalo per year. Well, we need to find out, though, how many buffalo were in 2050, because that's where this is going to start at, okay? So let's go find the number of buffalo in 2050. So using that first equation, so 112 plus 2.75 times 50 over 1 plus 0.002 times 50. And so if I calculated this right, this is 226.818 approximately. So that's our starting amount in 2050. So 226.818, and they said it's going to decline by 5 buffalo per year. And they said this is good from 50 less than t, less than or equal to 100. And so there's our piecewise function that'll take care of that entire century. All right, then 13 says grain is leaking through a hole in a storage bin at a constant rate of 6 cubic inches per minute. The grain forms a cone-shaped pile on the ground below. As it grows, the height of the cone always remains equal to the radius. If the cone is 2 feet tall now, how tall will it be in 1 hour? Note that the volume of a cone is pi over 3 r squared h. All right, so the grain is leaking through the hole at a constant rate of 6 cubic inches per minute. Cone-shaped pile on the ground as it grows, the height is equal to the radius. So I'm going to make note of that. All right, if the cone is 2 feet tall now, so wait a minute, we got an issue here. We got 1 in inches, 1 in feet. Let's just change the feet. 2 feet. Remember, there's 12 inches and 1 foot, so this is 24 inches. Let's change that. Okay, so it's 24 inches tall right now. How tall will it be in 1 hour? So we know the equation they gave us. They told us volume was equal to pi over 3 r squared h. But let's see, they told us about, they haven't told us about anything, whether it's the radius or the height. But we know that h and r equal, so since r squared is bigger, I'm just going to change my h to an r. So volume equals pi over 3 r squared times r. So volume equals pi over 3 r cubed. All right, so there's my equation. So let's talk about now. What's happening right now? What is the volume right now? Well, it told us that the cone is 2 feet tall. So that's our height, which is the same as our radius. So the volume is equal to pi over 3 times 24 cubed. And so I can just work that out. Now I'm just going to leave the pi as pi. So 24 cubed divided by 3. I know my volume is 4,608 pi inches cubed right now. Now it's increasing because that grain is leaking. And it's leaking at the rate of 6 cubic inches per minute. And we want to know the height in 1 hour. Okay, so 1 hour is 60 minutes. And so we know it's 6 inches cubed per 1 minute. And so we're going to multiply that times the 60 minutes. And so we should get 360 inches cubed. All right, so it started out at 4,608 pi inches cubed. In that 1 hour, it gained 360 inches cubed. So let's look at the total volume. So that's going to be the now plus the increase. Okay, so my now was 4,608 pi. Plus, we just did 360. And so I'm going to use my calculator. I'm going to put in that pi. So 4,608 times pi plus 360 gives me approximately 14,836.458 inches cubed. Now that I know the volume in that 1 hour, I can use that volume to find the height right now. All right, so now let's go find the height in 1 hour. Okay, so first thing I'm going to do is, if I'm looking for my height, I'm going to go through and work my equation. So remember, our equation was V is equal to pi over 3 r cubed, which we know the radius and height's the same thing, so I'm going to change that to h cubed. All right, I'm going to solve for h, so I'm going to multiply by 3, divide by pi, so h cubed is equal to 3v divided by pi, and then to get rid of the cubed, I'm going to take the cube root. So I know that h is equal to the cube root of 3v over pi. Now if I want the height in 1 hour, I already know its volume. So I'm going to take the cube root of 3 times the volume, that's at 14,836.458, divide that by pi, and find its cube root. And so I should end up with 24.197, and our height is in inches. And so I know we don't like the box, but I'm going to box this one so we don't lose it. And so there is our height in 1 hour. And that is the end of Unit 1.